In this video, we'll look at logarithms and their relationship to exponential functions. So, you have certainly experienced logarithms in high school in an algebraic sense, but in the real world, good examples of where this gets used is for stuff like earthquakes, so the Richter scale. And the idea here is that, so if there's an earthquake in California and it's a 4 on the Richter scale, and then there's another earthquake and it's a 5 on the Richter scale, then what's the difference between these? Well, the 5 is 10 times the power of the 4. So if you have an earthquake that's a magnitude 9, then it's 10 times a magnitude 8, 100 times a magnitude 7, 1,000 times a 6, 10,000 a 5, and 100,000 times a 4. So this gets really big really quickly. So earthquakes tend to get measured in a scale that works like this. So essentially what you're keeping track of is what the exponents are rather than what the sort of raw magnitude of it is. Decibel scale for the loudness of a sound works like this, and there's several others. Okay, so the word logarithm is kind of interesting. It's built of two Greek words, logos and arithmos. And the word logos means ratio, amongst other things, and the word arithmos, well, you probably guessed, that means something to do with numbers. So the logarithm is somehow a number that encapsulates an idea of a ratio. So for example, here, 5 is somehow 10 times more power than 4. So 5 is a number that really is expressing a ratio that has something to do with 10. Okay, so the way that this is related to exponential functions is oftentimes we would say something like this. So let's say 100 is 10 squared. So the way on the left is sort of the exponential view, and then the way that I'm going to write on the right is how to write this in a logarithmic view. So if I were to say that 100 is 10 squared, then this would be equivalent to saying that 2 is the log base 10 of 100. Okay, so again, 2 here is expressing the ratio that makes 100 or 10 and 100, so what the ratio is in a sort of exponential sense between 10 and 100. Okay, and so notice here that the 2 really is the exponent. Okay, and we could do similar things like this. These numbers don't have to necessarily be all nice like this. So for example, if we had something like the log base 4 of 2 equals 1/2. So here I've started with a logarithmic statement, and I want to unwrap this back to the exponential. And the way that I'm going to do that is I'm going to say 4 to the 1/2 equals 2. Okay, and that should make sense, right? Because what does 1/2 as an exponent mean? Well, we normally think of that as being a square root. So the parts here that match up is this part here is the base, and over here it's also the base. And then on this side, the thing that you take the logarithm of becomes the answer over here, and the answer on the other side becomes the thing that goes inside the exponent. So essentially what we're doing here is kind of reversing the role of the exponent and the answer, and that's what the logarithm function does. So what's really nice here is that the logarithm function will actually serve as an inverse for this exponentiation process. Okay, so here are a couple of examples with just numbers, so let's just sort of write this in more general notation. if we were to say that y equals a to the x, then the logarithmic equivalent of that would be to say that x is the log base a of y. Okay. Now there's two special bases that we commonly use. The first is the base of 10. And that's called the common logarithm. And the other one that we use is the natural logarithm. And there we use the base e, which if you'll remember is that about that 2.71828 blah 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 that we looked at last time. And this one gets a special notation. Well, both of them do actually. So if you see the logarithm without base explicitly written, then you're to assume that it's base 10. That can be different actually in some textbooks, but for us, a logarithm that doesn't have any base explicitly mentioned, you should assume it's log base 10. And then the natural logarithm, typically we write that ln instead of log base e, but they're the same thing. Okay, and these two are the only two that you'll notice that are on a calculator. So in class, one of the things we'll look at is, for example, like here, we've got this log base 4. If I wanted to compute this with a calculator, well, you might guess that we're stuck because there's no log base 4 button on a calculator, but there's an easy way to convert between them from bases that are funny like this to either the common base or the natural base, which typically are on calculators. Okay, so just a quick recap. For now, this may just be kind of a notational thing, and we'll talk about sort of the algebraic properties of sort of the functional view of this in class.